Okay, let's put this ArduStryfe board kit together here. I always like to start with resistors first. Kind of like with pancakes, the first ones you almost have to throw away because the iron's heating up and you get in your groove. And I'm going to go from highest value to lowest, and we've got two special resistors to start with. They're blue. They're 1% value, and they're part of a resistor divider circuit we're going to use to measure the battery voltage. So we want that to be an accurate measurement, so we're using high tolerance resistors, which are a little more expensive. Not much, but they are different. So we've got a 100K and a 10K, and when you plug in the math on that, it's a factor of 11, and so that allows a 5-volt system to do some monitoring of a higher voltage like our lithium cells. Okay, so this is not going to be a how to solder video, but in general, keep your iron tip nice and clean. Come in pressing down both the pad and the lead of the component, waiting just a minute. Waiting maybe 2 seconds. And then introducing some solder, and you should see it flow. And like I said, as your iron's heating up, it usually takes you a little bit of time to get the hang of it. And so yeah, resistors are fairly heat tolerant, and they also don't have a polarity, so they can go in either way. Okay, these are my favorites. These are Hecco CHP170 flush cuts, and they are fairly inexpensive, like $5 or $6. And they let us cut the leads down close to the board. You don't want to cut really close to the board because you can peel up your pads, but just cut them so that they're not sticking up. Okay, so we got our two special resistors out of the way. And then we've got a number of generic 10Ks, so these are like 5% value, run-of-the-mill, penny a piece. So we're using them for a couple of things. In the case of our MOSFET, we're using it to pull the base signal to ground, because we don't want that floating and accidentally turning on our motors when we're least expecting it. And then in a couple cases we're using them as pull-ups. So the signal, again, you don't want floating signals. You want them to either be high or low, and then when the event occurs, such as the button press or the dart fire, and that the signal is nice and clean and quick. And then another thing we're doing is we're doing some debouncing of the mechanical inputs, and so we have a resistor capacitor circuit that's helping with that. When you have a mechanical switch close, if you look at a very short time frame, like milliseconds, there's actually a number of electrical spikes as that signal transitions and steadies. And in the case of if we're using a microcontroller interrupt service routines, those get called when signal goes from high to low or low to high. And if we're experiencing those transients, then those service routines get called multiple times on short order, and that's not what we want. So you can add a little bit of circuitry to make them kind of break clean. And let's save this some headaches. As you can see now, our iron's up to temperature. Everything's kind of flowing smoothly. My mother once told me that she wished kids were like pancakes. You could throw the first one away because you make all your mistakes on it. And of course, being the oldest, I wasn't too enamored with that idea. Okay. Let's see. A lot of the times when I'm doing these bulk kind of solderings, I'll forget one or two, so those guys still need some solder. Just kind of walking into the forest and whacking on the trees. Okay, come back for him. I want to tell you what soldering from behind the camera is a little bit challenging. Can't quite get as close as you want. Trying to give you guys the front row seat, but sometimes that means the solder quality is a little less than perfect. Okay, so we're kind of working our way down the scale here. We've got a couple of 1K resistors, and they are also part of that debalance circuit, working with the 10Ks and some capacitors. So there's a 1K. Yeah, so we got two debalances. I'm trying to remember what we put them on. The rev switch is one, and the button is one. Those are the two mechanical inputs on a like the ArduStryfe. I've been developing. There's a number of other ones, like the pusher has a switch that definitely needs debalancing. Yeah, I originally started working on the ArduStryfe. I got one at a thrift store. This seemed pretty interesting, and it's got a motor-driven pusher, and that has a mechanical switch that shows when it's in the home position. And so trying to develop some algorithms for getting the number of select fire a little bit challenging, and since there's extra circuitry on that board, I switched over to try and get the Strife done first. A lot of my work has been centered around kind of beginning soldering projects, and even just doing the Strife here is a little bit more advanced than I'd hoped, but hopefully you're going to see this is not terribly difficult. Okay, so we've got one 330 ohm resistor, and this drives the, we have an LED, visible LED that goes right there, or it can be wired in anywhere on the system, but it needs a current limiting resistor, which goes right here. It has a forward voltage of about 2 volts, red and yellow, and usually green. And since you got a 5-volt system, you got to do a little current limiting to keep from blowing that thing up. And there's a formula for figuring that out based on the forward voltage of the resistor, which in the case of red is about 2, and then the current is about 10 milliamps. And then in the case of, we also have an infrared IR LED, which has a forward voltage of more like 3 and a current of about 50 milliamps. So we're using a 100 ohm resistor for him. and that's used for the dart detector. We're emitting infrared light and then monitoring it with a phototransistor, and then so when we see the break in the light, we assume a dart has started passing it, and when the dart finishes passing it, the light comes back on. And if we measure that interval of time and we know the length of the dart, then we can calculate the speed as well. So we got us not only detects the dart firing, but gives us the chronograph reading. Okay, so we got one more kind of low flat circular package, and it is the diode. Diodes allow current to flow one way. They're usually marked with a silver line. And in this case, it's called a kickback diode. So when your motor, when you turn the signal off on your, or the power off on a motor, the collapsing magnetic field can cause a very short spike in current going the opposite way, and that can actually damage your MOSFET. So what we do is we give it a little kind of short circuit path to send the electricity around the MOSFET, keep it from causing any trouble. So it's called a kickback diode. And its leads are a little bit thicker, so it takes a little more work on the soldering. Okay, we are cooking. So let's put in the start of the show here, which is the ATmega 328P, which is the same chip as used in the Arduino. So this is actually more powerful than the first computer I used as a kid. I had a Timex Sinclair ZX81. I think it had 1K of RAM and ran at 4 megahertz, and this has 32K of RAM and runs at 16 megahertz. And that I think I paid $150 for that computer, and this chip pair is about $2. So an IC package will always have either a dot or a divot. In this case, it's got both. And then your silk screen on your circuit board should have a dot or a divot. In that case, we've got the divot. And you saw me kind of bending these leads. When they come from the factory, they're splayed a little bit outward, and seem to have something to do with the way they're put into circuit boards and hold themselves. It's not real helpful for us hobbyists, because we got to get these to line up, all 28 of them, without bending any over. I'm not doing as well as I did last time. Okay, so we got those out. Check our orientation. Multi-lead packages, I always recommend just soldering 2 of the leads to start with, and I usually pick opposite corners and then come back and double check that your orientation matches the silk screen and that you've got your alignment the way you want it. And then we can nail it in place. It gets exponentially harder to fix a problem after you solder more than one lead in. So if you get it backwards, it's easy to get out with 2 leads. But once you've gone down this road here, it's exponentially harder to remove it. And I'll usually end up just clipping the leads off and desoldering them one at a time. Even, you know, it's like a $2 chip, but it's going to take me 5-10 minutes to get it unsoldered and resoldered, so sometimes you just gotta bite the bullet. I guess the moral of the story is, measure twice, cut once, or stitch in time saves 9. I don't know, something like that. It's getting late. We're getting kind of goofy here. Okay, so let's do our capacitors. So we've got 2 different values here. We've got a 1 microfarad and a 0.1 microfarad, and the lead spacing is actually the same, so you can mix those up. We don't want to. So let's start with the 1s. Get get those out of the way, and those are part of the power conditioning circuit for the 5-volt regulator. These are set usually by the data sheet. We'll have a example circuit with the values, and I just use what they recommended, and that helps stabilize that regulator system so you get a clean 5 volts out. And of course, so we need that 5 volts for the, so we're either going to be using the 6 volts from AA batteries, or like 7.2 volts from a lithium. The microcontroller needs either 5 volts or 3.3 volts to operate correctly, so that's why we're going to have a 5 volt system in this. And yeah, so microcontrollers like steady voltage, and so that's what these, one of these 0.1 microfarads is to help the chip. It's filtering the power signal, taking out any transients. And then the other 1 microfarads are part of the hardware debouncing. So one of the initial problems I ran into when you are trying to capture a signal like the dart passing, I'm sorry, I mean like a mechanical switch is where we have our that was. Let's do what I'd probably the hardest part on here. So I've thrown a little curveball at you. We've got a surface mount MOSFET, and I did that mainly to make because the package is so much smaller than a through hole, and I really didn't have enough room on the board to do everything I wanted to, so that's kind of why I'm subjecting you to this. But I hope what you'll see here is that it's really not that hard. Surface mount soldering is not scary. There's a large pad, and I'm going to introduce a little bit of solder on there, and then what we're going to do is kind of float this piece, so it'll burn your fingers, and you can see the pad on the back. So we're just going to come in here and reheat it and just kind of slide it up in here, and then I'm looking at the bottom leads. As soon as they get into position down there, we know we're good, and then just let it set. Well, I'm not convinced that's a good connection, so I'm going to come in and hit it again and just press down on it. Okay, I'm liking that a little. Okay, so now we just need to swing it around and get some solder on these 2 leads, and it's very similar to how we were doing the through holes. We're just touching the pad on the component lead and introducing a little bit of solder, and you should see it just wick right in there, and that's that. Okay, easy peasy. Let's see, what do we got for components left? So we've got a speaker here, a little piezo, gives us a beep on startup and can let us know that our battery's low. It does not have a polarity. Some piezo speakers do. These ones do not. Okay, we've got two components left on this side, I think. Oh, let's see, we didn't get our power regulator in yet, so we've got a couple of packages that look similar. We got 3 Hall effect sensors, which are going to go on the other side, and then we've got the power regulator, and I can't remember what it says on there. It's like a 1704. So anyway, make sure you get the right one. He's also got a little different lead spacing. And he's gonna, oh, let's see, so I've got here MCP 1702, and he's gonna drop in, so there's a flat face. The package shows the flat face towards the IC chip, so we'll drop him in like so. And then a lot of times I'll just splay these out just a little bit to hold them in place. And one at a time. Now these guys are close together, so you're going to have to be a little bit careful with your soldering. If you get too much solder on there, come back with solder wick. I'm assuming at some point I'll have to show you what solder wick looks like. But the other thing that's helpful is to, if you got like a solder or a flux pen, that will help you get a nice clean joint. And yeah, this is not real great soldering work because I'm behind the camera, but I believe it's going to do the deal. Okay, so we also have our resonator. This is drives the it's like a crystal, drives the frequency so the chip knows how fast to run. It has an internal 8 megahertz clock, but 16 using this crystal lets us run 16 megahertz, a little bit quicker. That's kind of interesting. So the chip itself can go to 20 megahertz, but in the original Arduino boards back in like 2005, the chips were only rated to 16 megahertz, I think. So that's why Arduino set that standard, and that's just always been 16, even though the chips are capable of running a little bit faster. When you get looking at what we're doing in the code, you'll realize how amazingly fast 16 megahertz is when you're doing stuff like measuring motor rotation, and the dart speed is still plenty fast. Let's see, so somewhere I had a fuse. Where's my fuse? Oh, here it should be. So stock ArduStryfe has a, I think it's a 1.6 amp fuse, and it's resettable. They heat up. So if you jam your flywheel motors, they start drawing their stall current, which is about 2.7 on AA's, and that'll cause the polyfuse to heat up and choke back the flow of current, and it'll save your motors. And so in our case, since we anticipate going to a lithium battery on the stock motors, it'll draw like 3.5 amps or more, 3.7 on startup. So we're gonna just bump up our fuse a little bit. I know a lot of modders will just cut the fuses out, and a lot of modders will blow up their motors, especially if you loan your blaster out to somebody who's not quite savvy enough to know not to pull the trigger when the darts quit coming out. So it's nice to have your fuses. Now, of course, if you're going to do something like aftermarket motors like Michel 2.0s, then you're going to need a higher fuse, because the startup current on aftermarket motors is exponentially higher. So a pair of Michels will pull somewhere 30-35 amps on startup, and of course that's going to whack this guy. Now this is one trick I'm not. So we're trying to get everything as flat as possible, and you saw me fold the resonator over, so we're going to fold this polyfuse over the diode. And again, we talked about the board layout constraints, and so I'm not terribly happy with that, but it's what we're going to have to do to get it so that it's going to go into the ArduStryfe with this side down. So we're trying to get everything as flat as possible. And we're done with this side of the board. So we're going to come over here and do our Hall effect sensors and our headers. Going to connect this to the world. So the Hall effect sensor is very thin packages, but you can see it's kind of a, there's a shape to it, and that's the side that's got the markings on it that tells what kind of chip it is. And again, we're going to be folding these over. So we've got the 3 legs here with the face towards the top, and down like so, and then fold over. So these guys I like because they are let's see, what's the term? Omnipolar, so they can detect a north or south pole. And on my original, my Geek Spinner project, which is a fidget spinner that uses a Hall sensor to detect the rotation, I wanted to use these, but it turns out they've actually got a little sleep circuit in them, so they're only taking measurements, I think it's like once every 100 milliseconds. And they do that just for power conservation. And so, like if you're looking at an event like a laptop lid opening or closing, 100 milliseconds is just fine. But when you're trying to measure the rotation of a fidget spinner, it's not going to work. So I had to go with a different sensor, and it could only detect this. I can't remember if it was the south pole, and that meant your magnets had to be in the correct orientation, which was kind of a hard thing to do, add a layer of complexity. So these guys have that 200 millisecond sleep cycle, and we're using these to, we're putting a magnet on the clip, and as the clip gets installed, there's a switch, the clip detect switch triggers, and then we know we can go check our Hall effect circuit and see if we've got a clip that we recognize. And since we've got three separate sensors, we can determine those 2 to the 3rd power, I don't know, computer math stuff. So basically 8 different configurations if you think about a 3-bit number, and since one of the bits is nothing, 0, 0, 0, then we can actually measure 7 clips, which gets us most of the Nerf clips. 6, a 10, a 12, a 22, 35. Of course, there's still a couple out there, like the 50. The mythical 50. Okay, so we've got those. And then someone was just pointing out to me the other day that the clips actually have ridges on them based on what capacity they are. So I wonder if Nerf at one point was thinking about having some kind of way to detect what clip was installed, maybe some switches. These little chips are about 70 cents a piece, so looking at, like some kind of large-scale manufacturing, that's kind of cost prohibitive. You see I didn't do a too great job of getting that one line there, but it's going to be fine. Okay, and along the top here we have all our headers, which are going to allow us to plug in. You could solder wires into these, but it's much easier, especially if you got to switch the board out or something, to be able to change things around. I'm going to start with the 4-pin one, which is for the display. It's labeled ITC, which is the communication protocol for the display. It has 4 pins of power, ground, and data and clock. And so you can see there is an alignment to the header that we have to get right. And then we've got to flip it over, and then this is probably the second most challenging soldering portion of this this board is getting these, because again they're very tight pitch. And so you can see I'm using a chisel tip, so I'm not using a fine tip, but just trying to control the amount of solder and the angle. And I think maybe I'll bust out some solder flux and show you. So yeah, I think we got it, but let's just come in and say I solder bridge this, because I'm pretty sure that's going to be a common thing. And you can either come in with solder braid and pull some of that up, or you can just see if my flux pen is working here. Add a little bit of flux, and then clean your tip so that you don't have a lot of solder on it, and just come in and try and pull it away. And as you reload your tip with solder, just take it off again. And we're back to nice clean joints. So there's two ways to kind of get around any issues you have. So that's one of the things you definitely want to check before we power this up, is that there's no bridges, especially between ground and power would be bad. Okay, so the 3-pin header is for the photoemitter section. Is kind of on the front end of the blaster. It's we're sending power to the IR LED, and then we're getting a signal back from the NPN transistor, which is pulled up to 5 volts on the board, and then there's the ground, the return line for both of those circuits. And then the remainder of these headers are 2-pin, and one of these is for a button or triggering the debug mode of the firmware. So as we bring the system up, we're going to put it into a debug mode so that we can verify each of the subsystems as we install them. Okay, just a couple more of these. Next one down the road here is for the jam door, and this one we're using we're using it to actually turn on and off the microcontroller. So the battery voltage actually passes through the switch here. So when the jam door is shut, the blaster will turn on. Oh man, so I completely missed the oh boy, so now we get to show you the solder wick. So I soldered 2 leads that weren't there. The pads are now covered, so similar to if we were going to desolder something. So the solder wick, solder has a affinity for the copper stranding. So you just hold it up and apply some heat, it comes right up. So I like using the wick more than the solder pump. Solder pump's a little tricky to do, and it doesn't work in a lot of occasions. Alright, let's go back and see if we can get the right ones this time. Yeah, this is kind of the problem with being behind the camera. But it gave me a chance to show you the solder wick. It's your friend. I use it all the time. Okay, one more header. And yeah, it's one of the reasons I like using the headers is just because it helps you keep the wiring much cleaner. Let you put the circuit board in place and then have the wires cut to the correct lengths, and so you'll see as it goes on, but it does add a little bit of work. And so now we've got our LED here, and I think I'm going to save this for later. So if we want to start this on the board, it goes in like that, but I like putting it in the blaster where it shines through the shell at the back, and we'll use that for determining when we're out of ammo. We're going to save that for later, and then we'll just wire those in. And then all that's left is the battery wires here. And then to see only other open holes, we have our two mechanical through-hole mounting, and we've got our ISP header and our FTDI header for programming. So our next step will be to get us some power, and we'll hook in the display and get this powered up, and it'll allow us to start checking our work out. And so as a final thing, I'll do this off camera, will be to come in and visually inspect all my solder joints to make sure I don't have any bridges or misses, and hopefully save us up, and then we'll just retouch up. Like that one looks like it needs a little extra work. Other than that, I think we're ready to go.